Good evening, everyone, and welcome back to week 3 of the tutorial session for the course Dynamical System and Control. Am I audible?
Yes, ma'am, you are audible.
Okay, thank you. So, in the last week, the recorded lectures that were uploaded covered various important topics. For example, it was shown how to find out the fundamental matrix solution for an autonomous system of the form x dot equals to ax, where if you need to find out the fundamental matrix solution given as xt, you need to find out the eigenvalues of a, then find out the basis solution, and then cascade them as column vectors. So for an n cross n system, it will go to xnt. So this will give you the fundamental matrix solution, and for system of this type, it is also shown that e to the power at is one of the fundamental matrix solution for the system x dot equals to ax. And then how to find this exponential? It can be find out using, if you calculate this matrix solution capital of xt, then in order to calculate e to the power at, you just have to, because any fundamental matrix solution can be written as xt into some constant, so for e to the power at, you have to replace this constant with inverse of the initial value of fundamental matrix solution, where 0 denotes the x of t calculated at initial condition or at t equals to 0. So this was the second topic that was covered. And then how to find out the solution xt for non-homogeneous system. So what are non-homogeneous systems? Systems of the form, if I write x dot t equals to axt plus, if there is a term ft here, then how to find out the solution for such systems? So the solution for such systems can be given as xt equals to, so obviously the solution for where a is constant can be given as x of 0, that is the value at initial condition, e to the power at, or you can write as the more generic form, the state transition matrix. State transition matrix phi t, or phi t minus t naught. Let's say this t naught is 0. So it is x of 0, phi of t, and plus phi t, t naught to t, phi s inverse fs ds. So this is how you can calculate the solution for non-homogeneous system. And we know for system of this form, phi t can be given as e to the power at. That is the state transition matrix. Then further, after finding out solution, we focused on the qualitative analysis of the system, where we can do analysis of the evolution of system trajectory using the critical points, or the what else we can call such points, equilibrium points. And how to define such points? So for system, for any dynamical system, okay, the equilibrium points can be found out by equating the dynamics to 0, okay, and those points which qualify for this, that is for all those points where x dot is 0, are called the equilibrium points. And then what further we covered about the stability analysis, when we call the solution to be stable or unstable. Okay, so what was the definition for stability? If I talk about the solution phi t, or let's call xt equals to ft, okay, for solution phi t, how we will define that this solution is stable? So for that there is an epsilon delta stability definition, and which is very important, and this should be kept in mind because it will be used very much in all the further lectures. So how you define stability? So generally for any system we define stability about the equilibrium point, and that equilibrium point we call as the solution. So for example, you have a system of the form x dot equals to fx, then we find out all the equilibrium points by equating x dot equals to 0, and then we want to know whether the solution xt, which is, let's say this gives you an equilibrium point eq, then I want to know whether the solution, this eq, is stable or not. So the stability basically provides you the notion of boundedness. Okay, so for example, for a scalar system, let's talk about, here is, let's suppose, your eq, equilibrium point. Then stability tells you that if you start nearby this solution or nearby this equilibrium point, and if you start delta neighborhood of this equilibrium point or solution, you are going to stay in epsilon neighborhood of this equilibrium point. So this epsilon can be within this or it can be outside of this, but there will be some epsilon. Okay, there will exist some epsilon for every delta, such that you are always going to stay within the epsilon neighborhood of this solution or equilibrium points. So this is how stability is defined. More generically, if you want to represent it mathematically, so we write it as the solution, let's call the solution as eqt or eq. It is said to be stable if for every epsilon, so for every epsilon there exists obviously epsilon is greater than 0, there exists a delta, and this delta can be function of epsilon such that every trajectory, or let's say every trajectory or every solution denoted as phi about this solution or equilibrium point is within the alpha if I start, T naught denotes if I start nearby this equilibrium point, delta in the delta neighborhood of this equilibrium point. So if I start, so if the trajectory starts in delta neighborhood of phi equilibrium point or any reference trajectory if you are talking about, so if your solution or if your trajectory starts nearby delta nearby of equilibrium point, you are going to stay epsilon neighborhood of that phi j for all t greater than equal to t naught, or if t naught is 0, then for all t greater than equal to 0. Okay, so this notion is very important for when we characterize when we do the qualitative analysis of the equilibrium points. Okay, so this was all about the week 3 recorded lectures. Now let's try to solve some problems related to these notions only. Okay, so let's start our first problem. Okay. Okay, so let's start with a very quick question. So consider a system which is given as x dot equals to 1, 3, 2, 0, 4, minus 1, minus 3, 2, 1, x, with initial condition xt naught equals to x naught it is given. Then comment on the solution, whether there will exist unique solution, infinitely many solution, or finitely many solutions. What can we comment about the solution x of t for this initial value problem? So what are the conditions for existence and uniqueness of any solution? It should be the right hand side, if I call it fx, it should be continuous and Lipschitz. Okay, so continuity, obviously there is no discontinuous point, and whether this is Lipschitz or not, obviously it is, because A is a constant matrix. So there always exists a unique solution for any initial value problem for an autonomous linear system. Okay, so if we have any autonomous system of this form, with initial condition given, there will always exist a unique solution.
Ma'am, I have a doubt here.
Yes.
Ma'am, suppose that the determinant of a matrix is 0. In that case, the solution should be unique or infinitely many.
For the determinant, so your determinant, it will be 0. So your
Yeah.
all the eigenvalues will be 0.
Yes. No, no, not all the eigenvalues. One of the eigenvalue is 0.
One of no, then only there will be unique solution.
Okay, okay.
Yes. Okay, now let's move on to another problem. So have you solved assignment problems for week 3? Have you gone through it? Anyone?
Yes, ma'am. A couple of problems I have solved, but not all.
Just attempted, ma'am. Don't know the correctness. I have to recheck.
Okay. Okay, so let's start with first problem. So I think the assignment problems for week 1, 2 and 3, those are very numerical based. So you have to do a lot of calculations in order to find out the solution. So here also I am trying to do those kind of problems only. Okay. So consider the differential equation x dot as yes, okay, x dot equals to a matrix 1 1 0 1 into x, and we have the initial condition given as minus 1 0. Find the generalized solution x of t. So please try it once. Okay, so what are the steps for solving for the generalized solution? What we have to do in step 1? Calculate all the eigenvalues. Okay, so what are the eigenvalues? Eigenvalues of, let's
1
call
comma
it
1.
1 comma 1, because it's a triangular matrix, so we need to calculate the diagonal elements will be the eigenvalues. So we have lambda 1 and lambda 2 both equal to 1. Now next what we have to do? So we have repeated eigenvalues. Now in step 2 what we have to do? We have to calculate the eigenvector such that this A minus, since lambda 1 equals to lambda 2, we can call it a minus lambda, sorry, I into v equals to 0. Okay, so what will be v for this case?
1 comma 0 ma'am, column
Yeah,
vector.
yeah, 1 comma 0 we can calculate, so let's call it v1, so it is 1 0. Okay, now we have repeated eigenvalues, so another eigenvector which is linearly independent we cannot calculate using this approach. So what we have to do, in the earlier session we saw that this e to the power at can be written as e to the power lambda t and a minus lambda it. Okay, and this can be expanded as an infinite series. We already saw that. Okay, okay, so using this we can find an eigenvector such that this a minus lambda I into v2 is not equal to 0, but this a minus lambda I square into v equals to 0. Okay, let's call it v2. That means, so this v2, if this is not equal to 0, that means this v2 is linearly independent of this v1. Okay, now so we have to square this term. What it will give us? A minus lambda I square. So it will be 0, sorry, it will be 0 0 0 1 into 0 1 0 0. Okay, into v2 equals to 0. So this is nothing but a 0 matrix, and a vector v2 we have to find out. That means the elements of v2 are arbitrary. We can choose any value of v2, but we have to choose v2 such that it is linearly independent of v1. So what choice we can make?
0 1 ma'am.
0 comma 1.
0 1. Yes, so v2 we can take as 0 1. So these are our eigenvectors. Now the solution corresponding to this one can be written as the solution x1t, let's call it, can be given as e to the power lambda t, and e to the power lambda is 1. Just a minute. Yes, so it is e to the power t 1 0. Okay, and now x2t we can find what it should be. Lambda is same, so e to the power t 0 1. Oh sorry, no, we have to find this. So e to the power, the solution x2t is e to the power at into v2, which is written as e to the power lambda t. And this expansion, in this expansion we have already seen that we have calculated it for this equal to 0, and that means all the further terms will also be 0, so we have to calculate up to first order. So it is I plus a minus I, because lambda is 1, into t into v2. So this will be the second second solution basis. So it is e to the power t 1 0, and a minus it will give you 0 1 0 0 t, and v2 we have calculated 0 1. So when you solve it, you will get x2t as you will get T1. So when you solve this, you will get this. Okay, now the generalized solution can be written as the linear combination of these two. So it is C1 of, the first one was ET10 and the second one is ET1. Okay, now find out the solution for this initial condition. Calculate C1 C2. Initial condition is -10. It is given that x0 is -10. So what will be C1 and C2 for this case? Anyone calculated?
C1 is -1 and
What will be C2?
C2 will be C2 will be 0.
C2 will be 0. Okay, because I have not calculated, so I trust these values. So xt, it will be minus et, and since C2 is 0, it will be 0. C2. Okay, so this will be your solution if the C1 C2 values are correct. Okay, now let's move on to another problem. Yes, so this question is related to fundamental matrix solution. So consider the system which is given as x dot equals to x dot equals to 1 1 0 0 minus 1 0 0 0 2 into x. Find out the fundamental matrix solution. Okay, let's call that xt. What will be xt for this case? So how to calculate fundamental matrix solution for linear autonomous system? So as I already briefed, we have to calculate the solution basis and then cascade them as column vectors. So that will give you x of t. Okay, so we have to follow the same procedure as before. Calculate the eigenvalues, calculate the eigenvectors, calculate the solution basis, and then cascade them as a column vector. The eigenvalues for this case will be, again it's a triangular matrix, so the diagonal elements will be the eigenvalues and these are distinct eigenvalues. So we just have to solve the eigenvector by equating this as 0 for each of the lambdas. So for lambda 1 equals to 1, what v1 we will get? So let's solve for lambda 1 equals to 1. It will give you, we have to put lambda equals to 1 here and solve for v. So that will give us 0 1 0 0 minus 2 0 0 0 1. Okay, and let's call it as v1 v2 v3 equals to 0. This means v3 is 0, v2 is 0, and v1 can be arbitrary. So one vector that we can choose is 1 0 0. Okay, next what will be for lambda equals to minus 1? So for lambda equals to minus 1, we get a minus lambda I as 2 1 0 0 0 0 and 0 0 3. Okay, so it will give us equations 2v1 plus v2 equals to 0 and v3 equals to 0. So we have the matrix, the vector v as third element 0. So v1 and v2 are dependent, so let's choose v2 as 2, then v1 can be given as minus 1. Okay, now let's calculate for the other eigenvalue was 2. For lambda 3 equals to 2, we get the equation, it is minus 1 1 0 0 minus 3 0. Okay, now if you solve it, you will get v as 0 0 1. Okay, so what are the solutions? So solution 1, what we can write as solution basis 1 will be, for lambda equals to 1, we have v as 1 0 0, so it is e to the power t 1 0 0. For x2t, what it will be, e to the power minus t and minus 1 2 0. For x3t, what it should be, e to the power 2t 0 0 1. Now what we have to do to find the fundamental matrix solution xt, we have to cascade them. So the first column will be formed using this, so it is e to the power t 0 0. Second will be this, that is minus e to the power minus t 2 e to the power minus t and 0, and the third will be 0 0 e to the power 2t. So this is your fundamental matrix solution for the given linear autonomous system. Okay, let's see another problem. Consider matrix A, which is given as 0 minus 3 3 0. Okay, find the exponential e to the power 80. How to find this exponential? How can we find the exponential e to the power 80? So we have to follow the same procedure. We have to calculate the fundamental matrix solution xt, and then calculate it for initial condition. So let's say that the initial time is 0. Calculate its inverse. So this will give you the exponential e to the power 80, and its proof is derived in the recorded lectures. You can refer to that. So this is how we can calculate. So first tell me, what are the eigenvalues for this matrix?
Plus minus 3 iota.
Yes. So lambdas will be imaginary. So lambda 1, or let's say lambda equals to plus minus 3i. Okay. So how to calculate generalized solution? Not generalized solution, how to find out the solution basis for complex eigenvalues? So because the complex eigenvalues always occur in conjugate, so we can pick any one, and we have to find a minus lambda I, same way as we did earlier. So let's take lambda equals to 3i. So it will give us a minus lambda I will be minus 3i minus 3, and it will be 3 minus 3i. Okay, and v1 v2 we have to calculate. So it will give us minus 3i v1 minus 3 v1 v2 equals to 0, and 3 v1 minus 3 I v2 equals to 0. So v1 equals to I times of v2. So what we can take any combination. We can take v2 as 1, so v1 will be I, or you can choose v2 as I, then v1 will be minus 1. Okay, you can pick any of these eigenvector. Then what we have to do, we have to write the yes, xt. So what will be solution then? It is obviously e to the power lambda t into v. Okay, now what is lambda? Lambda is 3it, and v is, let's pick this I1, so it is 0 1 plus I 1 0. Okay, if I am choosing this one, this can be written as this. Now e to the power 3it, what we can write it as? Cos 3t plus I sin 3t, and then this is, sorry, because the real and imaginary one both constitute for the solution eigenbasis. So we have to calculate for real one and then for the imaginary one. Now the real one will give us what will be the real part of this?
Cos 3t 0 1.
So if I say x1t as the real part of this, then x2t, another solution eigenbasis, will be imaginary of this. So let's find out the real. So real part will be given as cos 3t into 0. So it is 0. And this will also give us the real part because I square will be minus 1. So it is minus 3 sine 3t. Okay. And then this is cos 3t. Is it correct?
Yes, ma'am.
And what will be the imaginary part? This is equal to, what will be the imaginary part? The imaginary part will come from,
0
it will
and
be,
I sin 3t.
yeah, so it
0 and I
is
sin 3t.
cos 3t, right?
Okay, first term, okay, fine.
Because this will give us cos 3t. And then next imaginary will be sin 3t. Is it correct? I think so. Then what will be the fundamental matrix solution? We have to write them as cascade column vector. So it is minus sin 3t, cos 3t, cos 3t, and sin 3t. And then we have to find x of 0. So put t equals to 0, it will be 0, 1, 1 and 0. And then we have to calculate its inverse. What will be the inverse of this? It will be same. Then we can calculate the exponential e to the power at as xt x0 inverse. So what it will give us ultimately, since we have calculated each part of it, xt is here, x0 inverse is here. So when you multiply these two matrices, you will get, please take the calculation. If there is any mistake in the calculation, please let me know. Sin 3t and cos 3t. Okay, so this is how you can calculate the exponential or the state transition matrix, we generally call e to the power at as a state transition matrix, by using the fundamental matrix solution in this way. Okay. Okay, now let's move further. Okay, now let's move to problem for solving solution of non-homogeneous system. Yeah, okay, let's do this. So consider a non-homogeneous system of the form x dot equals to ax plus gt. Okay, where your a is given as 2 1 0 2 and gt is given as sin t cos t, and initial condition is you can take anything. Your initial condition is some constant value, let's call it as p, we can call. Okay, then calculate the complete solution for this system. How to proceed? Now since this matrix A is a constant matrix, okay, so the state transition matrix we can calculate for this e to the power 80, we can calculate, and the solution can be we can find using, so initial condition into state transition matrix. So this A is constant, so the state transition matrix will be e to the power 80, and then there will be another integral term because of this time varying function, so that will constitute the solution part in the form of, so we can write this as e to the power 8t minus, so phi inverse is nothing but, so initial time is 0, so we have to integrate from 0 to t. If it was something else, we have to write t naught, so it is given as t0. And what will be inverse of this state transition matrix? It will be nothing but e to the power minus 80 only. And now since we have to do integration, we replace t with s. No, so this is g, so g of s ds. Okay, so this will be the solution for this non-homogeneous system. So what are the things that we have to calculate? The only important thing that needs to be calculated is this state transition matrix e to the power 80. And since we have already solved so many problems of the state transition matrix, you can easily now calculate e to the power 80. And once you have calculated, you have to do this integration part. Okay, so this integration may take some time when this g is some sort of complex functions, but here we have the sinusoids, so we can easily do the integration also. Okay, so let me solve a few steps of this, then you can proceed further for this one. Now in order to calculate e to the power 80 or the state transition matrix, what we need to calculate first, obviously the eigenvalues. And since it is a triangular matrix, so eigenvalues are nothing but 2 2, which are repeated, and we have to proceed this way for the repeated eigenvalues, like we have done for this problem. Okay, for repeated eigenvalues we have to proceed in this way. Okay, so let's quickly see. We have lambda 1 lambda 2 equals to 2. Then first eigenvector we can calculate by solving a minus lambda I v equals to 0, and when you do this you will get your v1 as 1 0. Okay, now second eigenvector you have to calculate by solving square of this into v0, and when you do this you will get matrix of the form 0 0 0 0. Okay, so you have the you are independent to choose any value of v. Now since we have already choose the first eigenvector was 1 0, the linearly independent eigenvector will be nothing but 0 1. Okay, so now this in hand we have to find out xt. Before that we have to find out x1t. So it is e to the power 2t 10, and x2t, for x2t you have to do some calculation, so it is e to the power 2t I plus a minus 2i t into 0 1. Okay, so when you do this you will get okay. So let's take it as 3. Okay, so it is a minus 3 it, and this will be nothing but e to the power 3t t1, and xt can now be easily given as e to the power 3t0 t e to the power 3t and e to the power 3t. Okay, now next we need to calculate x0 inverse. So it is nothing but 1001. So it is identity, so its inverse will be same. And then e to the power 80 will be xt x0 inverse. This will give you the matrix e to the power 3t t to the power 3t 0 and e to the power 3t, the same as xt. Now what next we have to calculate to solve this integration? We have to calculate e to the power minus as. So e to the power minus as will be nothing but we have to replace t with minus s. So it is e to the power minus 3s minus s e to the power minus 3s 0 e to the power minus 3s. Okay, now we have everything in hand. We just need to write the solution and do the integration. So it is xt. So first let's write the generalized solution for this type of differential equation. E to the power minus as gs ds. Okay, so x0 was given as a constant p, and e to the power 80 we have calculated 3t t to the power 3t 0 e to the power 3t. Okay, so p will obviously be a 2 cross 1 vector. For that we need to write p here, because then only we can do a matrix multiplication. So let's write x0 here. Okay, so p is obviously a column vector of size 2 cross 1. So this multiplication will give you a column vector of size 2 cross 1, which is consistent with the solution xt. And now for this part, let's keep this e to the power 80 as it is and do the integration of this thing. Now we have e to the power minus as this, and gs was yeah, gs is, it is given as sin s and cos s. Now we need to multiply these two. When we multiply this, we will get it will be sin s minus s cos s and cos s. Okay, so this term needs to be calculated by doing the integration, and then we have to put the limit, and after doing everything we will get our solution xt. So how we will do this integration? Obviously the it's a column vector, so integration we can do individually for the upper term and then for the lower term. Okay, now when you do this integration, so these term will be, this term will be as it is, plus e to the power at, and when you do this integration what you will get, you will get, just writing it, it is something, it will be something like this. Sinus, and this term will be minus 3 cos s. Okay, and then you can put the limit from, the limit is from 0 to t, so this part will be same and it will give you finally the column vector 1 by 100 so there is a bit of calculation that you need to do for such type of problems. This will be the solution for this problem. Okay, and e to the power 80 you already calculated, so it will be a 2 cross 2 matrix and this is a 2 cross 1 column vector, so when you do the multiplication you will get a 2 cross 1 column vector. Okay, and then this term you have to add with this and that will give you the complete solution x of t. Okay, the only thing that needs to be remembered is that for such non-homogeneous dynamical system we need to calculate the state transition matrix e to the power at when A is a constant matrix, and then you have to remember how we write the solution for such non-homogeneous differential equation when A is constant, and then do every calculation that is needed. Okay, now in similar way we have another problem, and that you can proceed in the same way. So consider a non-homogeneous system where A is 0 1 1 0 and this gt is t e to the power t. You have to find the complete solution x of t, where x of 0 is 0 0. Okay, this will be a bit simpler because we have terms like t and e to the power t whose integration will be much easier than before. So if you want I can solve this problem also, but this will be the same way like before. The steps will be Same, only thing that we have to do is the calculations. So if you want, I can solve this problem, or we can skip this one and move to next problem.
Okay, ma'am, skip this one and next one.
Yeah, okay. Okay then. Yeah, okay. So here is a problem where it is given that consider the system Tx dot equals to Ax, wherein A is given as 2, 0, and it is -4 and -1. Okay, calculate the fundamental matrix solution. Okay, you don't need to calculate it like we did earlier. So tell me if xt will be, so let's say the option A is log t, or it is, you can say, e to the power a, or e to the power, okay, in this form you have to calculate, not the complete e to the power 80 thing you have to do. How can we proceed for this problem? Any idea? The system which is given to us is of the form Tx dot equals to Ax. Okay, now if you write x dot, it will be A by Tx. So we assume t is not equal to 0. Now this is of the form A by T, means there is, let's call it as a matrix B, which is a function of T. Okay, A by T we call it as B of T. So this is a non-autonomous system or a time varying system. How can we calculate the state transition matrix, or sorry, the fundamental matrix solution for such type of systems? Because here the matrix is not constant, it is time varying. So this will be same. Let's call it as calculate the state transition matrix. State transition matrix is also one of the fundamental matrix solution, because any fundamental matrix solution, if we have a fundamental matrix solution x1t, we can always find another fundamental matrix solution as x1 into some constant. Okay, so we can call it as state transition matrix also, because okay, now what is important here, for system of the form x dot equals to ax, what is the state transition matrix? If I call it as phi t, it is nothing but e to the power a dt. Okay, from 0 to t. So this will give, this always gives us e to the power at, because a is constant. Correct? Now where this a is time varying, and we cannot do this integration, because we know it is, we can only do the integration when this a of t1 and a of t2 are commuting. Commuting means this a of t1, a of t2 equals to a of t2 into a of t1. Now tell me whether this, so here we have a by t as the time varying coefficient. So whether this a by t is commuting or not. Can I write, because a is constant, can I write a by t1 into a by t2 as a by t2 into a by t1, because a in our case is this whole term. Okay, will these two be equal? Here a is constant. Tell me, anyone?
Yes,
Yes,
ma'am.
ma'am.
Both are equal.
Both are equal, obviously, because this denominator terms are just scalar values, so these both are equal to a minus a square minus a square, right? So this will be 0. Means this time varying term which is given in this question are commuting for time t1 t2. Then what we can write as a state transition matrix, if I call it phi t, the state transition matrix, now we can do this integration, right? Instead of a we have a by t into dt. So this will be our state transition matrix. This a is constant, we can take it out, and it is 1 by t dt. What it will give us? Integration of 1 by t is log of t, and this we can write as e to the power, this a we can take inside as power, okay. And this is nothing but we have log in the exponential, so it is equal to t to the power a. So which option is correct? The last one. Any doubt in this question?
No, ma'am.
Okay. If this was not the case, then it will not be easy to find the state transition matrix, because then the time varying terms will not be commuting. In this case, this time varying term was commuting, so this a we pulled out from the integration and just do the integration of the variable t. Otherwise we have to do all these expansions like it was mentioned in the recorded lectures, the Magnus expansion or the piano Baker series. That thing we have to use, and it is not easy to calculate the solution for such type of time varying systems. Now in the similar way you can calculate the solution for system of the form tx dot equals to ax plus tq, where you have a given as 1 2 0 minus 1. Okay, so here you have a non-homogeneous system, because so for this system you have to find out the solution xt. Okay, consider the initial condition t naught is x naught. Okay, so in order to calculate the solution or to find out the solution, what steps we have to follow? We need to find out the state transition matrix, obviously. And what will be the state transition matrix for this problem? We have already done it in the previous problem. Okay, this can be written as a by tx, and this will be t square. Now the particular solution, the solution will be, let's write it as the state transition matrix phi t into x naught, and then we have phi t from t naught to t phi s inverse, and then we have this term, let's call it ft, so it is fs ds. Okay, like we have done earlier. So no, we have actually transformed it, so our fs is this t square. So this is how we write the generalized solution for any non-homogeneous system. And for this type of problem, phi t we have already calculated in this previous question. So phi t for this one is absolute of, where it is, absolute of t to the power a. Okay, so this is nothing but t to the power a and x naught. Similarly, phi t is t to the power a. We have to do integration from t naught to t. So what is phi s inverse in this case? Phi t is t to the power a. What will be phi t inverse? Okay, it will be just t minus a, and instead of t we have to write s, so it is s minus a. And what is fs? Fs is s square into ds. So this solution can be written as x naught plus ta from t naught to t. So it is, since we have to multiply these two, so it will be 2y, because here it is a matrix, so it is s, it is 2y minus a into ds. So this will be the solution for this system. Obviously you can do the calculations, but the motive was to show how we can find out solutions for this type of problems. Okay, one last question for today. Consider a second order system where the dynamics is x1 dot as x1 x2 minus x1, and x2 dot is given as x1 cos pi by 2 x2. Find all the critical points or the equilibrium points for this system. How can we find out the equilibrium points? To find out the
By
equilibrium,
substituting x1 dot equals to 0 and x2 dot equals to 0.
yes. So we need to solve for x1, x2 such that this x1 dot is 0 and x2 dot is 0. So equating the first dynamics as 0 will give us x1 into x2 minus 1 as 0, and equating second dynamics as 0 will be this as 0. Okay, now let's see what values of x1 and x2 will make this 0. So this term can be made 0 by x1 equals to 0 or x2 as 1. What for this case? This also can be made 0 by x1 0 and x2. What will should be x2?
N.
Not
No.
not n but n plus 1 by 2. Odd numbers. Then what will be all the combinations that will make where n belongs to 0 1? Not 0 but 1. Okay, so what will be all the combinations of x1 and x2? So if I want to write equilibrium points, so if x1 is 0, then this will be 0 and this will be 0. That means x2 can be arbitrary. So let's write it as x2. So this gives us first set of equilibrium points. Can we make another set of equilibrium point? The first dynamics can be made 0 by x2 equals to 1. So x2 equals to 1 will make this 0 and it will also make this term 0. So that means x1 can be arbitrary. So we can write it as x1. Are there any other possibilities that will make both the dynamics 0 at the same time?
No, I feel, ma'am.
Yes. So how many equilibrium points we have for this system?
2.
No, but infinite. We have infinite equilibrium points, right? Because the first set tells us you take x1 as 0 and you take x2 as any value. So x2 any value means x2 can be anything. So there are infinite values of x2 with x1 equals to 0. So there are infinite possibilities for this one. So there are infinite number of equilibrium points. Another set tells us you take x1 anything and take x2 as 1. These gives us another infinite set of equilibrium points. So in total we have infinite number of equilibrium points for this one that depends on the value of x1 and x2.
Understood, ma'am.
So if you understood, tell me how many equilibrium points we have for this type of system, linear autonomous system. We have a not equals to 0. What values will qualify for equilibrium points? So we have to make this ax equal to 0. Now if a is not 0, then the only possibility for this to be 0 is the 0 vector, right?
Yes. X
equals
has to
to
be 0.
0.
Mhm.
So we have, for a linear autonomous system, we have the unique equilibrium, and that equilibrium is nothing but 0. Okay, so that's why um, when we further see the qualitative analysis, you will see that we will tell the stability of the system only about the origin, because equilibrium point is the origin vector. Okay, and that is unique. So for linear system, we have only one possibility of equilibrium point, that is the 0 vector. But for non-linear system, this is a non-linear system, we can have infinite number of equilibrium points. So based on the concept of equilibrium points, we will see how can we tell about the stability of the system, and that will be covered, I think, in the week 4. Okay, so that's all for today from my side. We will meet next week uh, to solve some more problems, and also I think from next week we can have some MATLAB examples also, in order to draw the face portraits, etc. That will be covered in the next week, so we can go through MATLAB examples also in order to plot the face portrait.
Ma'am, you will provide the MATLAB code.
I will show you how you can plot the face portraits if it comes in the next week. Then I will show you here how you can draw.
Okay, thank you.
Okay, then let's meet next week. Thank you
Okay,
for
ma'am.
joining.
Thank you.
Thank you,
Thank you,
ma'am.
ma'am.
We are leaving.